The points we have here were obtained by evaluating the quadratic function for the different values of x. We'll use the red points as a training set, the purple points as a test set, and observe how and when the underfitting or overfitting happens. Let's start with underfitting. Whether the model will generalize, overfit or underfit is in part dependent on its capacity, which is the model's ability to fit the wide variety of the functions. The blue line on the graph was obtained from performing the linear regression on this training data. But as mentioned earlier, the data was obtained from a quadratic function. First-degree polynomial, however, does not have enough capacity to capture the curvature of this data. Consequently, it is unable to obtain a low error value on the training set and generalize. Let's now look at the model which is able to fit and generalize for this data. The green plot was obtained by performing the second-degree polynomial regression on the data. We can see that it fits training data well and generalizes to the testing points. This is because the model's capacity is appropriate for the current task and the amount of the provided training data. The orange plot was obtained by fitting an 8th-degree polynomial to the data. What we see is that despite fitting the training data perfectly, it does not generalize to the test data. So while the training error is low, test error is still high. This is because the model's capacity is too high for the current task and the amount of the training data. This can sometimes be fixed by adding more training data. On this slide, we see the 8th-degree polynomial again, but trained on a larger data set. But if we keep overcomplicating the model, for example, if we try to fit the same data with a polynomial of degree 80, we will again run into the overfitting.